Hello, this is Dr. Christy Lukes, and this is the solution to Exam 2 for our Thermo 1 course. So let's look at the first page. On this one, this was one where you choose the most appropriate model for estimating the volume for these various cases. And so on the very first one here, what we have is a liquid that's undergoing a large change in temperature in a process for which a detailed design is required. So first of all, let's look at these. And I have these grouped so that the first two are appropriate for liquids only. This one is appropriate for liquids or solids. And these last three are only recommended for gases. Now, we did derive and discuss them with liquids, but then we came back and we said that they do a very poor job of estimating liquids, and so therefore we have these other methods that are better. So let's look at the first three for this liquid with a large change in temperature, and we need a detailed design. If we're using constant beta and kappa, that means that we think that there is virtually no change, very small changes in temperature or pressure. And so if we are saying that they're constant, then that's not appropriate for a large change. So our next one is the Ursin charts. Those ones allow us to look at changes in temperature and pressure. It is graphical, but there's a lot of detail to it. The last one is assuming the substance is incompressible, which means that I'm saying that the volume doesn't change. And if I think there's a large change in temperature and I'm looking for detailed design, then clearly the only answer for this one is B. Now, I will say that I did give partial credit for those who gave the answer A, because that will get you a good estimate, but it's not adequate for a detailed design. Now the next one is a gas being heated at atmospheric pressure, but it's only heated slightly. And we just need a reasonable estimate. So of these, we have the ideal gas law, the virial equation, cubic equations, or the Lee-Kessler tables. The ideal gas law is pretty good for atmospheric pressure. Most gases are going to be kind of ideal gas-like. And I'm just looking for a reasonable estimate, so that actually is your best answer. The virial equation is really never recommended. I mean, we use it theoretically because we're using it to just make sure that the other things we do are reasonable, but it's not ever going to be a good estimate. And then we have a high pressure process, I skipped one, a solid being heated at elevated pressure. And for solids, the only one that I have is to assume that the substance is incompressible. So volume doesn't change much for solids. The next one is a high pressure gas process with significant change in temperature and pressure. So I need something that's going to account for big changes in T and P. And I'm doing this in a detailed design calculation. Okay, so it's high pressure, which means it's not going to be likely to be ideal gas-like. And in this case, since I need a detailed design, really I'm looking for F as the answer. Now, I also did accept, instead of F, I accepted G, the Lee-Kessler. It's not quite as good, but it's okay. And our last one was a high-pressure gas process with significant change in temperature and pressure, so that part stays the same. It's already been designed using software, and what I want to do is verify the calculations by hand. Payne-Robinson or those other cubic equations of state are difficult to do by hand. So therefore, usually what we do if we're just checking things, the best choice would be to go with G. Now, I did accept E or F for that, but they're not as good of choices. E because it's really just not very good, and F because you're going to work very hard for just verifying a calculation. Okay, so that completes problem 1, and if you had the other versions of the test, then you'll just have these same things in different orders. Now question 2. Question 2 is about heat of reaction. And we've been given various heats of reaction for these various parts, and we want to know what happens for A plus B goes to E. Well, if you add these up, then what you end up with is 2 A's and 2 B's and a C and a D makes C and D and 2 E's. Okay, now C and D cancels from both sides, so 2A plus 2B equals 2E. And what I actually want is A plus B. So first I added these up, and if I add these up, I have negative 100, negative 125, so negative 225 kilojoules per mole. But now then, instead of 2A plus 2B makes 2E, I want A plus B makes E, and so therefore I need to divide by 2, and so the answer is negative 112.5 kilojoules per mole. Now the final question on this page is a gas flowing in an internally reversible steady flow process with one inlet and one exit, and heat is transferring into the system. Now there are different ways that you can analyze this, but we want to know specific entropy at the exit, and the easiest is that ds is dq reversible over temperature. And if it is reversible, then delta S is that Q reversible over temperature. And I know temperature is always positive because it's absolute temperature, and I said heat is transferring into the system, so both of these are positive. Delta means exit minus inlet, and that needs to be positive because both Q and T were positive, so therefore SE must be greater than SI.